In this video I'm using the linear sensor of an old printer to detect motion of a homemade linear drive. As demonstrated in the previous video, a 6mm threaded rod converts the rotational movement of the electric motor into linear movement. The movement of the carriage is measured with a dial indicator. When turning the plywood wheel by hand, the drive can be directed to the 0 point precisely. The movement of the carriage is detected by scanning a plastic stripe with a fine line pattern. The plastic stripe is mounted on the mechanics with a fixed end and a free end that is stretching the band through a steel spring. The line pattern on the plastic stripe is scanned by two transmissive photosensors attached on the carriage. The switching state of the sensor outputs is indicated by two LEDs. Whenever there is a high signal on an input of the Arduino, the accordant LED is turned on. If the carriage starts moving to the left LED is turned on first. Secondly, the right LED is also turned on. Thirdly, the left LED is turned off. And finally, the right LED is also turned off. That cycle starts over again if the carriage continues moving to the left. As demonstrated in my video about rotary encoders, that pattern can be used to detect the direction of motion. A full turn of the indicator equals a linear movement of 1mm, thus 1000 micrometers. 24 pulses are generated at the inputs of the Arduino each millimeter of movement. Accordingly, 1 pulse equals a movement of 42 micrometers. An H-bridge and an electric motor can be used to turn the plywood disc and so the threaded rod by the Arduino Uno. Through the feedback of the linear motion sensor, the control loop is closed. Whenever the set point gets changed through a command from the host computer, the carriage moves the transmitted number of pulses to the right or to the left. As calculated before, the carriage should move 42 micrometers with each step. As you can see, the movement occurs not in totally equal steps. The lower limit is ruled by the minimal movement needed to change the state at one of the sensor inputs at the Arduino. Let's move the carriage to the left until both LEDs are turned off, and back to the right until the right LED is turned on again, which happens after a movement of less than 5 micrometers. To get the largest step width, the carriage is driven close to 0 coming from right until both LEDs are turned off, and moved further to the left until the sensor state changes again. The distance travelled is less than 50 micrometers. Same as in the previous video about this linear drive, the backlash is measured under side load using the homemade spring scale with the electric motor turned off. The maximum deflection is 130 micrometers, and we get 45 micrometers after the carriage is released. The mechanics isn't well adjusted to demonstrate the effects. If the measurement is done again with the electric motor turned on, the control loop of the Arduino moves the carriage contrary to the deflection caused by the spring scale whenever the state at one of the inputs changes. The Arduino compensates the backlash, at least if that movement is larger than the minimal resolution of the linear sensor. Now the measured backlash is no more than 35 micrometers, which is approximately the interval between two different sensor states. We also get a deflection no more than that interval if the carriage is moving to 0 coming from left, moving to the right for another 256 pulses, changing direction and finally moving to the left the same number of pulses, we get just 10 micrometers. With a second carriage sliding on rubber gaskets, side load during movement is applied to the main carriage. When repeating the measurement with changing direction under side load, we get an error of 15 micrometers, which is once again inside the interval of minimal sensor resolution. If the carriage is directed to the right for 4096 pulses, which equals approximately 20 centimeters of movement, and back to the left the same number of pulses, the movement ends at the starting point, at least with an error no more than the minimal sensor interval. Can we compensate all weak points of the linear drive using that sensor? Well, there are limitations. As demonstrated before, when deflecting the carriage slowly, the Arduino can limit the error to 50 micrometers. The motor speed and the clock speed of the microcontroller limit the speed of the control loop. When hammering on the carriage, the maximum deflection is more than 200 micrometers. When hammering with high frequency on the carriage, the input signals on the Arduino are changing too fast, so that some pulses are skipped. That causes a drift of the carriage to the right, although there was no change in set point. When using a strong, high-speed motor with a poorly adjusted mechanics, thus with noticeable backlash, the control loop starts oscillating around the set point. You can eliminate that in changing the software code. You have to define an interval around the set point where the motor power is reduced or cut off completely. The oscillations disappear by losing some accuracy. The control loop starts counterbalancing the deflection not until the error exceeds 100 micrometers. You can lower that interval when having a good, smoothly running mechanics with low backlash. Even an excellent linear sensor won't turn your poor mechanics into a good CNC machine. With the home-built sensor disk on the threaded rod, the step width is less than 10 micrometers. The resolution of this sensor stripe is too bad to get better results. Industrial CNC machines often have high-resolution linear sensors, which are very pricey for good reasons. You can stretch the thin plastic stripe by pulling on the free end. Quality sensors must be more sturdy. You must also consider thermal expansion when going below the range of 50 micrometers. The way you attach the sensor on your mechanics also matters. If the dial indicator, the fixed end of threaded rod and sensor stripe are on the left, we get an error of less than 50 micrometers when bending the mechanics by hand. Whenever the manual deflection exceeds that interval, the control loop reduces the error. If the sensor stripe is mounted with the free end on the left, the error exceeds 100 micrometers. As you can see, the control loop boosts the manually induced error because the sensor stripe is now deflected to the right. If you don't need a resolution of less than 50 micrometers for your application, and if your mechanics isn't too bad, you get a cost-efficient linear sensor by disassembling a broken printer. Read more about linear drives, sensors and some applications on the project page. Thanks for watching and I'll be back.